Classical Physics Tutoring, Chapter 5, Section 5, Electrical Engineering. Now, electrical engineering is, the foundation is Maxwell's equation. The Maxwell's equation defines all the electrical engineering component and the rules about how to design circuit and electronics. So, if you go through the Maxwell's equation, from there you learn how to use that to get every basics of electrical engineering. Then you're ready to go electrical engineering. We don't go into too deep on the electrical engineering, but all the basic stuff we're going to cover here. For example, capacitor. Capacitors, basically you put the V, so potential V, which is phi R, remember, in the Maxwell's equation. So convention is a little bar and the long bar. Long bar is skinnier, little one is thicker. And this is potential you're giving to one conductor, and another conductor goes to the negative voltage. And this can be earthed. Okay, so this is the capacitor C. Okay, so this voltage generate the electric field E. So E is the gradient phi, so it's going to be V over L. This is simplified gradient, right? It's divided by length L. And because divergent E equals rho epsilon, okay, total Q epsilon is area and E. So you establish the equation here. Sorry, this is S, area, because rho is a surface charge density, right? Yeah. So S V over L equals Q epsilon, and the Q over V become the S epsilon L. And definition of capacitance is the total charge over V, right? So this is the definition of capacitance. The capacitance is proportional to the area. Larger the area, it's bigger, and the larger the dielectric constant is larger. But larger the L distance, is the capacitance small. You put this plate together close, then capacitance is larger. So what they do is they make a capacitance. They use the plastic sheets and the metal on the both sides. So the sheet width is as thin as possible. But when you make it thin, what happens is there is a breakdown voltage. When you apply volt, if it's too thin, it breaks down and the electricity goes through. This plastic usually insulator, but it's a breakdown. So when you have a capacitor, it specifies how much voltage you can add, the maximum voltage. That's the breakdown voltage of the insulator. Okay. Then capacitor value, the microfarad. Okay. So that's a usually capacitor is. Okay. Now this is a not real product, but the physical product. You have radius A, conductor. What is a capacitor? So you apply V. Where's the ground? Well, this go against infinite distance. Suppose it's 0 volt. So you have a battery here like this to the infinite distance. Okay. So since phi equals Q 4 pi epsilon R, right? That at the distance A, it's going to be A. So this is voltage. So voltage, Q over voltage is the capacitance, right? So capacitance is going to be 4 pi A epsilon. Now we didn't calculate the energy. Energy stored on the single side is the E times D, and E we have this one, so we calculate half of CV square. But remember, entire capacitance is going to be 2U because you have a negative charge on this side accumulated. So it's going to be CV square. That's the entire capacitance energy. Okay. So the student often ask, why there's no 1 over 2 in the capacitor? Because you have two conductor on the both sides. If single conductor, this is correct. That's what you learn in physics. But electrical engineer always use this because practically capacitor you measure between positive and negative nodes. And this kind of capacitor is, well, ideal capacitor used only by physics, right? And the in order to estimate charge Q on a standard long conductor, this equation you can use, right? The Q is going to be CV. You know the capacitors, this one, and voltage you apply, then you know how much Q is accumulated. Okay, but it's not the kind of capacitor you use in electronic circuit. And there is a line capacitor. You have a single line, the AB charged with Q. The single line, how much? This is a line capacitor. Where it's used, it's a signal transmission line, has a capacitor, distributed capacitor here like this. Okay, and also it had a distributed inductance. We go through inductance later. And in this configuration, when you apply some alternate voltage, what's happened to the output? Okay, that's the kind of problem we use for this line capacitance. So this long transmission line is like, say you have a cable TV, has a long cable going to the house, and in order to maximize the signal speed, you increase the frequency here, and here, can you get that frequency? Well, if you have a distributed capacitance inductance, you have to do some calculation to see what kind of signal you get at the end of the long cable. Okay, that's the electrical engineering problem. Now, what's happened when you cascade capacitance in series, right? So you know it's going to be total capacitance 1 over total capacitance is going to be C1 plus C2 1. The reason? C is Q over V, right? So 1 over C is V over Q. And if you have a V1 and a V2, V1 plus V2 is total V, and this V1 is Q over C1 plus Q over C2. So V over Q is going to be C1 plus C2. So total capacitance is going to be, this is 1 over C. When you put in parallel, what's happened? The cap A, cap B, okay? So CA plus CB is going to be total capacitance, right? So this is like a physically, you have a extra area, but distance is different. But they are just summation of just area, but capacitance, okay? You use the same method, this one, to prove that. Now inductance is how many magnetic field is generated, right? So the key equation is this guy, dB dt, and A is NV. The I, Ampere's law tells you how much I, if you have n turn, n times I, and I is going to be the magnetic field and area and d, this distance, and that's going to be B d mu, okay? And so now you know the relationship between I and B for the inductance, but you have to take a derivative on the B over time to get the inductance. The combined equation is going to be n square A over D di dt. Okay, so this is the definition of inductance, L. So V equals L di dt. So whatever the current, alternate current, you take a time derivative times L is going to be the voltage across this inductance. Okay, so that's a definition of L. Now going back to C, the Q is integral of time, right? So when you have a Q equals CV, you take a derivative on both sides. So the integral of this is current. The current is C dB dt. Okay, so whatever the voltage, alternate voltage you apply here to the capacitance, take a time derivatives and multiply by C. It's going to be the I, alternate current. So you see here, it's opposite relationship. Capacitor I equals C dV dt. Inductance V equals L di dt. Okay, so you know what's happened if you have a capacitance and inductance together. It's going to create the second degree derivatives, and you have to solve the equation for d square dt square, right? Okay, so but electrical engineering has a very easy way to handle this kind of differential equation, because all the circuit diagram is linear differential equation. They convert into very simple format using complex number, and that's the part of engineering department you will learn in engineering if you do electrical engineering. Okay, so the Ohm's law is easy, right? Ohm's law is V equals Ri, no derivative involved. It's just linear. In the in the real world, you increase the voltage, I is going to change, like suddenly high temperature go like that, and depend on the characteristic of resistance. So there is a range. You can claim this equation, okay? And also R is typically the function of temperature, and those all specify the resistance component. See, you have a resistor, this is a lead metal, and has a color code, right? And the color code tells you the first 2 or 3 digit and times plus minus percentage, how many the accurate or not, okay? And the general characteristic of temperature is in the catalog. So everything will be consideration when you design very extreme condition, like if you're going to use this for circuit diagram, which is used on the moon, which go like 200 degrees C to minus 200 degrees C. The totally it's going to be off from this equation. Then all the circuit diagram you design is not valid for the outside of range. And the commercial range typically goes 0 to 40 degree or so. The military range can go up to 80 degree and minus 20 degree. So it's extended range because military use the more severe condition. If you design the circuit in this range and you bring the military equipment to the very cold place or desert, then it's all fail, right? So that's the electrical engineers consider those to design. Now Kirchhoff's law. Kirchhoff is a German sound is Kirchhoff's law. Okay, when I say that in the classroom, everybody laugh. What's a Kirchhoff's? That's the German's way to read it. In English, they call Kirchhoff's law, and the Kirchhoff's law is basically use the basic physics to solve the circuit problem. Okay, because you take this loop and add up all the voltage along this loop, it's come back, so it's going to be 0, right? And you take this loop, and this equation is made by I in each branch. This is I2, this is I1. So each branch has I and R's known. So you solve this linear equation, you can find I. Okay. Or another fact is you take this node and add up all the I coming into this. It should be 0, which is this. Suppose you have unknown V1, V2, so and so, or in this case use E1 and E2, and E1 divided by this is going to give this I, and you add this all I together in each equation, and you can solve this linear equation to find out I1 to I whatever, the E, I'm sorry, and this one is I, and these are equivalent. They are equivalent method, and sometimes node is simpler, sometimes loop is simpler, depending on configuration of the circuit. Okay, so the linear equation is a multi-variable linear equation. So the electrical engineering, they need to solve this very quick to analyze the circuit. Suppose you have 100 component linear equation, will be 100 component matrix, and linear equations is basically matrix equation. Say the matrix is A, and you multiply X equals B. So in this is the B, and we create a matrix, and the X is E1, E2, En. That's X. And A we create from this equation, and B is going to be from this. Okay, so we can solve the equation quickly if we know inverse matrix of A. Okay, so that's why the multivariable linear equation, how to solve it in the linear algebra in the math class, become very important for electrical engineering. Okay, and what's happened is you can't do that for the transistor. How do you do that? Okay, for the small signal, transistor can be made very ideal way. This input E in is going to be some beta E in out, so we convert that into a linear element. So if you have a transistor, many hundred of transistors in a circuit, and you say here's the input, you put the input, what's happened to the output, and that can be analyzed by linearizing non-linear electronic component. Okay, so that's a kind of things you do in electrical engineering. It's very exciting, many different technique of designing electronics you will learn in electrical engineering. So I hope, if you are going to this direction, the physics is the base always. Then you will learn a lot of add-on in electrical engineering. I hope you like this video, and if you like, subscribe.